Good afternoon. My name is John Kim, and I'm currently doing a project for my physics class. And I've decided to do my project on radioactive dating. And just to give a brief introduction, radioactive dating is the process of dating objects such as rocks and organic materials by utilizing radioactive isotopes, which I will be covering more in depth later on in the presentation. So I've decided to do this presentation because to me it was actually one of the harder topics to grasp during physics, and I was hoping to be able to break it down in an easier way for future students to understand. This is also an interesting topic for me because I'll be attending dental school next month, and I've found out that radioisotopes are actually widely used in dentistry as a research tool or for imaging techniques. So, for example, radioisotopes can help with determining the permeability in tooth structure to see what kinds of materials are able to penetrate our very hard teeth. To get started, as you can see in this picture that I found from Scientific Quaker blog, you can kind of see how radioactive dating works. So to start off, to answer the big question, what is a radioisotope? Essentially, a radioisotope is an unstable version of an element. And when something is unstable, it's not going to want to stay the same, if that makes sense. To make a quick analogy, you can kind of picture someone hanging onto a pull-up bar. To that person, they are in an unstable position, so they're going to want to eventually come back down to the ground. So radioisotopes work in a similar way, and they will spontaneously break down over time, and in doing so will emit energy in the form of radiation as they become more stable. So over on this side, you can see the radioisotope carbon-14, which is an unstable version of the element carbon. And basically these living organisms, such as this horse and this tree, they will absorb carbon-14 throughout their lifetimes. And when these organisms die and are buried, their remains will slowly start to lose the carbon-14 by way of radioactive decay. This is essentially what radioactive dating is based on. And researchers will basically track the amount of a radioactive isotope that is remaining in order to estimate the age of an object. In the case of carbon-14, as you see down here in this picture, it will undergo beta decay, where the radioisotope will emit a beta particle in the form of an electron, and it will turn into a more stable element, such as nitrogen-14. So one key term that we need to understand here is half-life, represented by T and then 1/2. And half-life is essentially the amount of time that it takes for a radioisotope to decay into half of its original amount. In the case of carbon-14, its half-life is depicted to be around 5,730 years, which means that after this time period, 50% of the carbon-14 will be remaining, while 50% of the carbon-14 will have decayed into nitrogen-14. And on this picture above here, you can see that I've depicted the key equation for the law of radioactive decay, which is necessary to calculate the age of an object. And in this equation, N is going to be the number of radioactive nuclei remaining at a specific time. N0 is the original number of radioactive nuclei at time 0. E is just the base of natural log, and the lowercase lambda is going to be the decay constant. On the right-hand side here, you can see that I've reorganized this equation to be able to calculate the age of an object, which is represented by the variable t. So now that we've went over the law of radioactive decay, we can go ahead and try to do a little example of estimating the age of an object through this PhET simulator. As you can see, the PhET simulator provides a certain probe which allows you to measure the amount of remaining carbon-14 or uranium-238. For the purpose of this project, we will be utilizing carbon-14, and we will be trying to estimate the age of this house. So we'll take our probe here, and it is stating that the house has a 99.1% amount of carbon-14. So let's go ahead and utilize the equation that I just went over to try to estimate the age of this house. So from the simulator, we've obtained a carbon-14 percentage of 99.1 from the house. And basically what I did here was just simply convert that percentage to decimal form, and I've plugged in the 0.991 value for our n over n0 variable here. And then as well as for the half-life value in our decay constant, I've plugged in the half-life of 5,730 years for carbon-14 down here. And plugging this all into a calculator, we were able to obtain a value of 74.8 years. So let's go ahead and try to plug this value into the simulator. So we're back on the simulator, going to plug in our value of 74.8 years. And as you can see, that is a very good estimate of how old this house is. You could also go up here and use this arrow to kind of get to the correct percentage that your probe tells you, and it will give you an estimate as well. So please feel free to try the simulator, and you guys can even go ahead and try using the uranium-238 probe for these different objects such as these rocks. However, do keep in mind that uranium-238 does have a different half-life than carbon-14, so the numbers being plugged into the equation will be different. So just to close out this presentation, I really do believe that radioactive dating and the use of radioisotopes has a very wide application in society. As mentioned previously, radioisotopes play a big role in the medical field, whether that's for dentistry or for medical imaging techniques. And there are still new radioisotopes being discovered to this day. So I think it's really safe to say that future technologies revolving around radioisotopes will only continue to expand and become more advanced. Well, that is it, and I hope you enjoyed my presentation on radioactive dating and radioisotopes. Thank you.